these things interact quite nicely, so I hope I have time to speak about that too. Right, so of course the promise of AI, we won't have to work anymore. In particular, I won't have to do AI research anymore because AI can just do it for us. It's great.
High times.
And yeah, AI is also like biological bodies, so maybe they can explore the galaxy to a large extent, which we can. So it's just a little question of how do we actually build them. And the approach that we take in our group is to like start in a top-down manner, like with a foundational theory. I'm not claiming by any means that this is like the only valid approach to AI, but I'm just going to try to motivate why this approach makes sense. So foundational theories have been very useful in other scientific areas. So for example, mathematics had Frankel set theory and personal logic, which gave it a lot more solid foundations and turned into proper science before it was basically just intuitions, if you will. Computer science would of course not be anywhere near what it is today without Turing machines and lambda calculus. Physics has quantum mechanics and relativity theory. Chemistry has quantum electrodynamics, I'm not sure about that. Biology has evolution. Social science has decision theory and game theory. So I think it's fair to say that for most scientific fields, having a foundational theory really helps making the field more mature. There can be many reasons for this, but I think it gives like a common language, common goal, common understanding of what we're trying to do. So when you have a small, narrow result, you know like where to fit this result into the grand goal. One more point I'd like to make about this is that even if the thing you're studying seems very complex on the face of it, like intelligence might seem like a very complex thing, humans seem very complex, and in particular our brain, it can still be some very simple principles that generate this. So there, for example, this Mandelbrot set in the background looks very, very complicated, but it's very, very simple rules underneath generating it. So perhaps it's the same with intelligence. Even though it looks super complicated, there might be a simple, elegant theory underneath. So intelligence is obviously something very interesting. People have tried to study it scientifically from very many different approaches. Humans, or like the cognitive psychology, behaviorism, philosophy of mind, neuroscience, linguistics, anthropology, which all concern themselves with like human intelligence in one way or another. There's machine learning, logic, and computer science, which are more formal approaches to making machines intelligent. And there's biological evolution, how did intelligence evolve, and economics, how do intelligent agents interact. If you want to like have some structure in this space, you can think about whether these theories concern with human behavior, describing human behavior, or whether they're trying to like nail down the correct behavior. And another distinction is between whether they consider something with thinking, such as cognitive science, how do humans think, or whether they concern themselves with acting, like how do humans act, Turing tests and behaviors, computer science. I think AI pretty clearly fits into the fourth quadrant. It's about doing agents do the right thing. We don't care if the human, or if the AI thinks exactly like a human, or whether it acts exactly like a human. We care that it solves the goal. So we want an AI that does the right thing. That's the goal of AI. Zooming in a little bit on AI, we have like a deduction-centered approach and an induction-centered approach. Deduction-centered is based on logical symbolical reasoning. As a logical specification, what it's supposed to do, perhaps medical expert system, try to infer a disease from symptoms, chess playing agent, trying to find winning move. In contrast, we have the induction-centered systems, which are based on probability theory and machine learning, and usually hard to specify an explicit goal for them. Instead, we like give them reward when they do something good, and they're just trying to get this reward and learn what we like them to do. good examples are AlphaGo and DQ learning. So AlphaGo recently won against the best human Go players, I'm sure you know. And DQM learned to play Atari games as well as a human, using machine learning techniques to a large extent. Induction-centered approaches tend to be more robust to noise and uncertainty. They tend to have less of a grounding problem, connecting like concepts in their head to the real world, because the concepts are developed themselves, by the agent themselves. And most importantly for this talk, with the induction-centered approach, we can actually construct a foundational theory for AI. No one has managed to do this for an induction-centered approach. But yeah, so foundational theory for AI is a theory that tells you what is the right thing to do in an unknown environment. It's hard to give a general answer to this without a really strong sense of induction. So that's a little bit of background, and I'm now going to explain the UEI theory, which basically says what is the right thing to do in an unknown environment. So UEI is this theory, it's a foundational theory for AI, and it answers this question, what is the right thing to do? It consists of these 4 components, roughly. There's the framework, which says how an agent interacts with the environment. There's the learning component, which is Solomon induction. There's the goal component, which is basically a maximized reward. And there's the planning component, which is fairly simple. Right, so I'm just going to go through these different components in order and then put them all together in the X agent. So the framework consists of an agent interacting with an environment. This can, for example, be a robot interacting with the real world, or a chess-playing agent playing chess, or a stock trading agent buying and selling stocks. So the agent takes actions. If it's the robot, it moves its arms and limbs, and sees some kind of percept in return, which is denoted E here. For the robot, this might be like a visual image, or a camera sensor. For the chess-playing agent, an action could be move the chess piece, and the percept could be like the new state of the chessboard. For the stock trading agent, the action would be buy or sell a stock, and the percept would be some kind of price index. These interactions go on in cycles. So first the agent takes an action A1, and the environment responds to the percept B1, action takes an action E2, act A2, environment responds to E2, and so on. So it creates a sequence of the interaction. And we call this interaction sequence a history. And the history up until time t is denoted with this A written together with an E, and the subscript less than t means that this is the history up until time t. The set of all histories is denoted with this A times E star. So that's the sequence, the set of all sequences you can create interleaving actions with percepts. Just to give you some examples, if we have the vacuum cleaning world, the percepts can be dirt or no dirt, and the actions can be suck dirt, move left, or move right. For the stock trading agent, the percept might be some real number, the price of the stock, and the action can be buy or sell. But it's really a very, very general framework. You can model essentially any agent interacting with essentially any environment in this framework. Formally, an agent is defined as a policy that maps histories to new actions. So after some history, AT, the agent pi takes action AT, which is equal to pi of the system. So pi, the agent, is just a function that maps histories, what has happened in the past, to the next action. The environment is the dual thing. It takes the history and the agent's latest action and gives the agent a percept in return. We generally allow stochastic environments, and we could allow stochastic agents too, but it's not really necessary. So environments are actually distributions, and this mu of ET, that's the probability for percept ET given this. An agent, it shows really poorly the red color, but the agent interacting with an environment creates this kind of tree, where first the agent takes an action. Depending on what the action is, you branch the tree depending on the percept, the environment gives back, and so on. And the point I want to make is that this second percept, E2, can depend on everything that has happened before. So the second percept can depend on the first action, or the 1,000 percepts down the line can depend on the first action. So we make no Markov assumptions or anything like that. And that's important because this is how the real world works. If I say dig down a treasure in my backyard today, then I'm going to find it if I dig 10 years later. So it's like the real world is not Markov, and this is reflected in our formulas. Just to compare this a little bit to the MDP framework, which is the standard basis of traditional reinforcement learning. In this framework, agents transition between states by taking actions. And the environment specifies, given a state and an action, which new state will you be in, S prime, and what reward will you get on the way there. And the policy is just a map in which state you take which action. The history framework is actually a lot more general. So just to compare the two, with histories, we have the percept that we see every time step, and in the state-based MDP framework, we have a state and a reward that we see every time steps. It's easy to see that histories are at least as general, because we could just let the percept E be a state and a reward. But we can have the percept be many other things, so histories are much more general. In particular, it's easy to have hidden states with histories. There's nothing that says that this percept that the agent sees at time step reveals everything about the hidden state, or about the state. We could do the same thing with MDPs, and then we get COMDPs, which is sort of like a more complicated version of MDPs. Histories also allows us to have worlds with an infinite number of states, like the real world has an infinite number of states, and this is something that's typically never considered in the standard reinforcement learning framework. Environments can also be non-stationary, and this means, for example, if I'm a self-driving car, and I make a sharp wheel turn in summer, and good road conditions, then I'm going to turn the car. But if I do the same thing in winter, and there's like super road conditions, then the result will be something completely different. So the result of an action might be different in different time steps. And this is sort of automatically allowed for this environment's view. It's just a distribution that depends on the entire past. But which is a little bit harder to incorporate in the MDP framework. It can be done, but it's just like an additional complexity added to it. Finally, an agent can just be defined as a policy when using histories, but in MDPs, an agent must be defined as a sequence of policies in order to incorporate learning. So for example, the agent would start with a random policy, and then as it gains more experience, the policy would change in order to be more directed to rewards. But when using histories, all the information the agent has is encoded in the history, so the policy itself can be learned, which is just nice intentionally. So all this generality comes to a price. It makes learning a little bit harder. In an MDP, such as this one, you can just return to the same state an infinite number of times, and after you've been in the state many times, you will know how this state works. When we're using histories, you never know if you return to the same state. Just see longer and longer histories, so there's no returning to the same thing. So learning needs to be much more sophisticated. You might think it's actually impossible, but it's not. And that's one of the amazing things with this theory. It tells us how to learn despite this super general setup. So that's the next topic, learning. How to learn in this super general framework. So the agent, you can think of it as like a newborn baby. It just can take actions and it sees some kind of precepts in return. And from this interaction, it needs to figure out some structure of the world. And of course, it's pretty hard. But it's also possible because like babies do it. And of course, it's important that the agent can learn because it must learn in order to be able to predict consequences of its action, and it must predict in order to be able to plan, and it must plan in order to act intelligently. So like, learning is this crucial first step, right? So it must learn the true environment from interacting with it in some way. The true environment is nuclear. So how do we learn? This learning or induction problem is really old philosophical problem, so philosophers have been thinking about this for a couple of millennia at least. And they have actually come up with some useful principles. Don't always do that. So there's Occams Razor, which says that if you have multiple hypotheses that are all consistent with your data, you should generally prefer the simplest of them that is consistent with your data. So for example, relativity theory might sound like a super complicated theory, but it's actually the simplest theory that's consistent with observational data about these things. So this seems to work pretty well. Epicurus is this ancient Greek philosopher who has almost the opposite principle. He says that if you have multiple hypotheses that are all consistent with your data, then you need to keep all of them. Because if you don't have any data that discards your theory, then you must keep it. You must keep it as a possibility. Does these principles make sense, I think, intuitively? There's also Bayes' rule, which says how to update your belief in a hypothesis given some data. And the input to Bayes' rule, the crucial input, is the prior, what's my prior probability before seeing any data in the hypothesis, and what class, this curly H, should I consider? What is the class of all possible hypotheses? These are the two sort of crucial inputs to Bayes' rule. If we have these inputs, the likelihood is usually easy, and we can know exactly how likely we should consider a hypothesis given our observational data. So Bayes' rule is really great and it's been very influential, but it does rely on this prior, knowing this prior, and knowing this class of hypothesis. So how can we solve these problems? What is the class of hypothesis, and what is the prior? The answer to these questions come from a kind of unexpected directions. Alan Turing invented this universal Turing machine. Machine basically can compute anything that's computable, also known as programming language. So what we can do with these Turing machines or programming languages is we can say that a hypothesis about the environment is just a computer program. Since computer programs can do anything that's at all possible to do effectively, using computer programs as a hypothesis, we're basically considering all possible environment hypotheses. So So we're very much in line with Epicurus' principle. Another neat thing about computer programs is that we can check if a computer program matches our experience so far. So let's say we've encountered some history, we've taken some actions, A up to time t, and we've seen some percepts, E up to time t. We can check if a given computer program is consistent with what we've seen so far, simply by giving the actions as input to the program and checking whether the output is exactly the percepts we've seen. If the output of the program exactly matches the percepts we've seen, then we say that the program is consistent. And if it is, then it's a consistent hypothesis, and if it's not, then we discard it. Similarly, if we want to use the computer program to predict the future, we just input the next action we have in mind, and we check what is the output of percept from this program. So this way we can use programs to predict and to plan. And finally, a really neat thing about computer programs is that they have a length. It's just like written some programming language, and we can just check how many bytes did it take to write this program. And that's what we call the length of the program. And we can say that the prior probability of a computer program P being the true environment should be 2 to the negative length of the program. This might seem a little bit arbitrary, but it isn't. So combining all these principles, we get Solomonov induction. Solomonov basically combines Epicurus' principle, use all programs. Occams Razor weights simple programs, short programs, higher than long programs. Obviously covers the areas of Turing and base rule in how to update the belief in a computer program based on data. Yes, question?
The environment is usually, it would lead to a stochastic percept.
Right.
So a computer program would also have to incorporate this stochastic feature.
Right.
So how can you check it for consistency?
Right, that's an excellent question. So we built this induction principle based on computer programs that are deterministic. And I will show you a result in like the next 2 slides, which shows that despite we base this principle on deterministic programs, they still handle stochastic environments really well, which is really surprising and like pretty cool. So, but that's in the next 2 slides. First, let me just introduce this Solomonov factor universal distribution. So the universal distribution, the universal probability of seeing some percept sequence given some action sequence, is just the sum over all programs, and the programs weighted by 2 to the negative length, the prior probability. Let me just give you an example of that before going on. So for example, seeing 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, given that I take exactly those actions, that's a high probability, because there is a simple computer program which outputs exactly this percept sequence on this input sequence, namely the program that just mirrors input to output. So seeing something simple, or seeing something that's very predictable from the actions, that has high probability. In contrast, seeing something random has comparatively low probability, because in order to have a computer program that outputs exactly this sequence on this non-informative input, you must include the entire sequence inside the computer program, and that's going to make the computer program long. So a priori, it's less likely to see random sequences than structured sequences. Question?
So if I remember correctly, the length is a strong function of how you choose to represent the program.
Yes.
Have you figured out a general way to represent that gets around that notation?
Right. Our standard answer to that is that you should use some natural programming language, say C or Python. But there is certainly some indeterminism in there, like which programming language to use, and it can have impacts, yes. Right, so that's some examples. Basically, structured environments are more likely because they have short computer programs. So, yeah, we follow basically Occam because we have simpler program high weight. At Curious, we have more programs based on how we discard programs, ensuring we have computer environments, or we basically said that. One thing is that what we're usually interested in is to predict the next precept given some history and action. And we can compute this conditional probability with just the standard rule of conditional probability. So, with that in place, we can now describe this very impressive learning result by Solomonov. It's very unfortunate that the red is almost invisible. So it's m of 0 given the history minus mu of 0 given the history. I hope you can almost read that.
Can you turn off the front lights or anything there, Tom?
Oh, that's a good idea. Any idea how?
There are light switches over there next to the whiteboard. You can try those.
There was some light control.
I'm just going to let you talk.
Listen.
Try this. No, doesn't work. Yeah, anyway, it's the universal distribution of 0 given the history minus the true distribution mu of 0 given the history. So what this theorem states is that you take any computable environment mu, you don't know it, and you interact with this environment mu by taking action and seeing percepts. And then you compare what probability does the universal distribution give to the next percept being 0 to the probability that the true probability of the next percept being 0. And what happens is that these two estimates converge fast. So the Solomonov prediction will converge to the true environment's prediction very fast. K of mu is the complexity of the environment, the Kolmogorov complexity of the environment. So the bound is weaker, the more complex the environment is. So K of mu is basically the shortest computer program describing mu. So anyway, we can say that the prediction error at time t, that's like the different probability, how different is the universal probability of the next percept from the true probability of the next percept. So that's a prediction error that the universal distribution makes. And we'll try to plot them here. In the beginning, m doesn't know anything about the true environment mu, so it will predict something which isn't related to the truth. But pretty soon, the prediction of m will converge to the truth. And the convergence is so fast that the total error, the area between these two graphs, will actually be finite. So you act in this environment for an infinite lifetime, and the total error you make of your entire lifetime is finite. Yes, question.
What about in non-stationary environments, or do you capture all possible ways the rules could change from the beginning?
Yes, even non-stationary environments, they can be really any environment. Any environment that can be described by a finite computer program, a computable environment. Yes?
When the number of history samples just go up each time it takes an action, and then does the whole system grind to a halt over time?
Sorry, once again, I didn't hear you.
So as it takes more actions and it builds up more histories, it's going to adapt. But then each time it has to perform a search, it has to go through a large number of histories. So won't it eventually grind to a halt?
Are you concerned about computational aspects?
Yeah.
Yes. Yes, this is not very efficient. This is more like, it's in fact incomputable to compute them. The value of this is more that it gives a conceptual and like mathematical understanding of what is the right thing to do. That's the goal. And then like in the second part I will describe like how we can approximate this. But for now this is not computable, not really practical. Anyway, an agent that is based on this universal distribution can basically learn any computable environment. And this result works, amazingly, even if the environment is stochastic. Even though M was based on deterministic computer programs, it still works in stochastic environments.
And sorry.
Yep.
K of mu cannot be infinity as well?
If K of mu is infinite, if the environment cannot be described even by a stochastic computer program, then just the result is vacuous. If the right-hand side is infinity, then the bound is vacuous.
So does a stochastic computer program then assume a random number generator, a real one? I don't understand how you get a finite number of errors in a stochastic environment.
Right, so the point is that, you don't need to say what the correct next bit will be. You don't need, let's say the environment is a coin flip environment, right? So the environment every time flips a coin. But then the environment doesn't know either what the next bit will be. So the environment gives 50% probability to heads, 50% probability to tails.
All you have to do is produce that distribution, not separate.
Yeah, so all you need to do is produce a distribution. Yeah.
And so you said K is the complexity of the program. So how do you decide that? Is there how do you define that complexity? So
Right, so K of mu here, that's the Komodoro complexity of the environment mu. And that's defined as the length of the shortest computer program that computes mu. More questions? Okay.
This is perhaps a better question when you get to your actual approximation.
Ah.
But if you run into two programs for K of mu, both of which are similar, like same or very similarly sized,
Okay.
what in your framework is the decision structure between picking them for the sake of the model? Or does picking between them not matter for the sake of the model?
Either they're going to be functionally equivalent, in which case it doesn't matter, or they are going to be different, and then at some point you are going to distinguish between them.
Okay, but is it just, I guess, up to the history, the way it plays out, then which one is chosen?
Yeah, pretty much. Yeah.
Could you remind me what 0 is the value of again? That's E of t.
Yeah, that's E of t, right. What is the probability that E of t is 0?
So here it's are we assuming that the environment only ever gives a 0 or a 1?
Yeah, that's implicit. Yes.
So my understanding is you can get some pretty good random number generators with some pretty short programs.
Right.
Is this algorithm actually good at figuring out the program of random number generators?
Right, because this just assumes away all the like computational complexity theory stuff. In practice that would be really hard, but in theory it's easy.
I see. I mean, it would need a tremendous amount of data.
Yeah.
I see. Okay.
Or rather a tremendous amount of computation power. Yeah. So I think we should move on. So we have this agent, and it can learn any computable environment, which is really great. So what should it use all this knowledge for? The answer we give to this question is it should maximize reward. So we assume that the percept that the agent gets at every time step is composed of one observation part and one reward part. And the reward part is just a real number between 0 and 1. So for example, if this is a robot, the observation will be like some visual image, and the reward will be a number indicating how happy its human owner is with it at this point. Another example is of the deep Q learning algorithm, DQN, playing Atari games. In this case, the observation was just the screen of the Atari game, and the reward was the score of the game. So the goal of the agent is to maximize the return, that is the sum of all the rewards it's going to get in the future. And to make sure this sum is finite, we introduce this discount parameter, gamma, which is less than 1. And then we downweigh future rewards by gamma. So the first reward is fully weighted, the second reward is multiplied by gamma, the third reward is multiplied by gamma squared, and so on. So it's a geometric discount. This ensures the sum being finite. And it also makes the agent care more about the near future rather than what happens 1,000 years from now, which is generally good.
And what's wrong with infinite reward? Oh, sorry.
Right. Yes. What's wrong with infinite reward? One problem is that in that case you get the same infinite sum if you get 0.1 reward at every time step as if you get 1 reward at every time step, because both are in infinity. So it's hard to compare infinite sums. Yeah, it's much easier to compare finite sums. Yeah, that's a good question. One more thing I wanted to say actually about this slide is that you can basically encode any goal as a reward signal. You just give the agent reward for doing the goal and no reward for not doing it. Reward for winning the chess game, no reward for losing the chess game. Reward for giving me a beer when I'm tired, no reward for not doing that. Yeah. So basically any goal can be formatted as this reward. So we're still general. Right. So return, that's the sum of all the rewards. And the expected return, that's called value. So the value of an agent pi, or policy pi, in an environment mu, that's just the expected return that the agent gets following this policy pi in this environment mu. So one way to think about this is like through these recursions, the value of being at this top node, that's the value of being in this node that you get after taking your first action. And the value of being in this point that you get to taking your first action, that depends on the whatever the environment gets to, which node the environment gets you to, what probability, and then this sort of average over those values of those points below and so on. So, yeah, it's basically just expected return value. It's a standard reinforcement learning concept. So the agent tries to be good in expectation, basically. Finally, the planning part of AGI, the last component. It's really quite simple, much simpler than the learning part. With this discount parameter gamma, we get what's called an effective horizon. So basically what happens with these geometric sums is that the tail of the sum, all the elements after some point m, this entire tail will be almost 0 because the gamma pushes this part of the sum down to 0 so fast. So the return for some infinite future is basically the same as the return for the first m time steps from now. This makes planning a lot easier because you just need to look m time steps ahead, and you can just think about all the things you can do within those m time steps. And you can think about the best thing to do, and yeah, that's the best thing to do. So conceptually, planning is actually very, very easy. I'm not saying this is a computationally efficient way of doing planning, but conceptually, it's easy to find the right thing to do in this setup. Another way to express this principle for planning is to say that the optimal action is the output of this formula. Where basically always take the best action with the max operators and expectations with respect to the environment with the summations and probabilities.
Did you say earlier that this policy may not be computable?
Yes, I mean, if the environment mu is computable, then you can find optimal policy here.
Yes.
Yeah. But what I'm going to get to right now is putting all these things together. That's called AGI-16, because in the real world, we don't know what the true environment is. So the idea is that we replace the true environment mu, which is unknown, with this universal distribution m. And then we tell the agent to be optimal with respect to the universal distribution m. So the policy AGI-16 is the best policy with respect to the universal distribution m. Since this universal distribution m learns any computable environment, being optimal with respect to m is, after a while, the same thing as being optimal with respect to true environments. At least that's the idea. So basically you get this one-line formula, which is like the thing below there, for the optimal behavior in an unknown environment. And here we've been basically tying together the Solomon induction with maximizing reward and this simple planning mechanism, expect nice. No, it's not computable. So we learn in computable environments. What we do is we basically act base optimally with respect to base rule. We have this one equation for artificial general intelligence. And the only thing that prevents us from taking over the world is computation. Yeah.
The other would be a policy to establish what the rewards are for any specific action.
Right.
Yeah.
That is not necessary here.
Yeah.
Sure.
Like, what are some examples of how to establish a reward system?
Right. I mean, if you have a chess playing agent, it's easy, right? You just give it reward for winning and no reward for losing. If you want a more general agent, the way I like to think about it is maybe I have a button that I can press, say, every hour. I'm so and so happy with you right now. And then the agent just tries to learn what does Tom like, and if it's really intelligent, it's going to be really good at predicting that, and it's going to make me super happy, ideally. And there's like some questions and problems with this, but yeah.
Could the rewards also be outsourced to some sort of like cost-benefit analysis thing, so that in like a more real-world simulation environment, rather than just have a you did good, you did bad, you have a more nuanced you did mostly good, or you did pretty damn bad but not completely terrible?
Like this reward doesn't have to be 0 or 1.
Right.
It can be any real number in between.
Right.
So yeah, you can like have a graded response. Yeah. Yep.
So it sounds like in any kind of real practice, in any kind of even toy universe that kind of simulates the real world, it's going to make the kind of mistakes that does the things that please you now but doesn't recommend you brush your teeth.
Right.
And 30 years down the road you pay the penalty.
Yeah.
But it didn't have time to learn that that was going to happen.
Right.
Because it doesn't have any read the literature, it doesn't have any learn from the culture around it.
Right. Yeah, that's potentially a problem. I think this depends on this, where did I put it? This discount parameter gamma, right? If we put this discount parameter so that it does care what happens in 30 years as well, maybe it will actually take time to read literature in order to be sure to optimize the reward also 30 years into the future. But yeah.
And that seems like that's what parents are for.
Right. Yeah. Yeah.
Also, something like brushing your teeth is very low cost.
Right.
So you wouldn't have to change very much.
Right. You would have to realize that there's some value into that, but yeah, sure. Yeah. So what I would like to do now is just have a 3-minute break where you just like discuss with your neighbor if there's anything more unclear, and then I'm going to go on with some other stuff. So just like a 3-minute break, and then we continue.
How fast is it going to decrease? You don't worry about 100 years, you worry more about near
So is there any questions? Yes.
So you have an MVP framework when you're doing this action percept history.
Yeah.
So
that obviously gets untenable, and I think you kind of talked about that you're going to have approximations for that.
Right.
Typically, even in I'd say more other reinforcement learning domains, say when you do robotics, you throw MVPs out the window and you have data coming in, you convert it to some sort of features, and
Right.
good enough, you hope that your state is capturing everything it needs to right now.
Right.
Kind of thing. So how is this different than what we practically do?
Right. I mean, it's a theoretical framework that tries to be general, basically, using these histories. Sort of the minimal assumption we can make. I don't know enough about the practical applications and what people do in various, yeah. Yeah.
Yeah, I was wondering about the prediction. Like, prediction isn't much good without the ratio of one probability to another.
Right.
So if going this way is 5 times better than going that way. Why would you actually need a reward? Would you automatically go 5 times that way because it was probabilistically better?
So probabilities are enough if you just want to know the truth. But if you want the agent to not just know the truth, but to also do something useful, we need to reward it to do something and not reward it for other things.
The reward just be the greater probability? I mean, it doesn't need a lollipop.
Sure.
It needs you to tell it this is your reward. And
Right.
if you had one ratio 5 times better than other,
Yeah.
that could be its reward. So
Yeah.
wouldn't that make it easier?
That would make it easier. There is actually a knowledge-seeking agent that has been developed according to exactly this principle, or at least something along the lines you say, I think.
It seems like that was closer to Ray's idea.
Yeah,
of
that's
the whole thing,
possible.
the importance of the ratio.
Uh-huh.
It's not just prediction, but is a prediction good?
Right.
So it seems like you might be able to incorporate that
Yeah.
better without, and not have all this reward stuff.
Sure.
What do you think?
I think rewards are good. I'm not sure how to motivate it better.
I mean,
Yeah.
we call that a reward.
Yeah. Yeah.
Well,
I'm
it
not
has to
sure.
classify events that it wants before it can determine probabilities and select the events with the highest probabilities.
Right. But why would we want an agent to have events with the highest probability? That's not fair. Anyway,
I
next.
think reward function prevents the Buddha states of an agent which understand everything and do nothing.
Right.
So
Sure.
it can predict with very high precision, but have no motivation to act in this environment.
Yep.
That's
But if you tell it, I mean, you're the guy that's telling it what the reward is.
so
If you
if
tell it that your reward is based on how probable that action is.
so you mean the reward should be a function of
Of the ratio of the probabilities.
Oh, it's an interesting idea.
It seems like that's.
then you get a
That's the
Buddha state.
direction Reagan took.
Then you get a Buddha states. An agent who will not act.
Yes.
The 2 to the minus length of the program.
Yes.
You said there was, I mean, it seems sort of natural, but you said there was some intuition behind why you picked that rather than, I don't know, something else. Maybe 3 to the minus length of the program, or?
Yeah, I mean, it comes from the fact that programs are encoded in bits, right? So, yeah, and you also need, you also need the whole thing to sum to less than 1. Yeah. We can maybe discuss more. Any other questions? Yep. Just
E is reward in E because you have sequences of A's and E's, which are the history.
Right.
And presumably the rewards are part of the E.
Yep. Yep. That's the assumption we make.
And so when you're summing, are you actually summing the rewards that are in the E's?
Yeah, that's exactly what we do.
I see. Okay.
Yeah. Good question. All right. So let's move on to what we can use this theory for. So some of the major selling points of having this theory, even though it's incomputable, not directly useful, is that it gives us like a high-level blueprint or inspiration for design of agents. It tells us what is the right thing to do in some mathematical sense, and then we can try to use this as inspiration for creating practical agents. Another thing is that it gives a common terminology in goal formulation. We try to build agents that actually does this thing, thing. We won't be close, but at least it's the point you aim for. The other thing I mentioned before, I think, is we can, if we know what the optimal behavior is, or we can characterize the optimal behavior in various ways, we can actually predict the behavior of agents we haven't built yet, agents we are too dumb to build so far. This can be a good safety thing. Appreciation of fundamental challenges, I'll get back to that later. And we can also measure the intelligence of the system by seeing how close does it come to IC, and this gives us some kind of sense of progress in how much progress do we make in AI. So this is just like some applications of having this theory. I'm going to start with approximations. So what we think about this is like creating intelligence is this big maze, very complicated, but IX at least gives us like a point. This is where we want to go. Doesn't tell us how to go there, but at least it's a point to aim for. So how can we approximate IC? There are three fairly different, or actually very different approaches to approximate IC. The first is the most direct, MCIX-CTW. It takes Solomonov induction and finds an approximation for Solomonov induction, and it takes the expected max planning, this clearly infeasible thing of exploring the entire future search tree, and steps ahead, and makes an efficient version of that, and then puts them together, then you have MCIX-CTW, a practical version of IC, basically. A very different approach is feature reinforcement learning, where we try to move away from these states. So our histories, like we have these histories which are hard to learn from, but if we can infer from a history which state we're actually in, then we could use principles that are used in normal MDPs. So that's the idea of feature reinforcement learning. Model-free IXC is tries to combine induction and planning into one learning step and doesn't plan at all. And I'll speak about each of them now for a bit. So let's start with the most direct approach, MCIX-CTW. So this expect the max planning algorithm, it effectively works by exploring the entire search tree m steps ahead. And that takes exponential time, and that's not good. We can never make a practical agent that way. So the natural idea is that instead of exploring the entire search tree, we just stimulate paths. Let's assume I take this action, and then the environment responds with something, and then I just take this other random action, and the environment responds with something, and then we just get like various simulations ahead in the future. Far from comprehensive, but just like various data points of what could happen in various trajectories. And if you average the rewards that we get on these like random trajectories down to the future, if we average the rewards from those, we get an approximation of the value. And the more samples we have, the better this approximation. Hope this makes sense.
We start from current state every time.
Yeah, we always start from the current state. Yep. So this is an anytime algorithm. We can just sample for as much as we have time for, and then when we don't have any more time, we have to act, then we just base our action on the current average. Monte Carlo tree search is an algorithm which does this very cleverly. Became famous for its good performance in ComputerGo, where we have this massive search tree, so future nodes, maybe 400 steps deep. In this case, it was very efficient. So the idea is basically that you want to. It's clear when you simulate one of these trajectories down to the future, right? It's clear that the percepts should be sampled according to like your belief about the environment. How will the environment react to this random action? But the agent itself is picking the actions. So it has some knowledge about which actions it should take. And it wants to focus most of its cognitive attention to most of the simulations on paths that are related to action that it will take, probably. So yeah, work quickly. Let's say I'm in the supermarket, and there's an apple and a banana and a rotten tomato. And I'm deciding which one to buy. I'm pretty sure I won't buy the rotten tomato because it looks really disgusting. So I'm going to focus most of my cognitive attention in deciding between the apple and between the banana. Because those are sort of plausible choices. So I want to spend most of my cognitive resources there. I also want to spend some resources on like thinking about the tomato. Because, well, it might have some strange, useful use. It's kind of a bandit problem. You can view it as a bandit problem for those who know what that is. And from the bandit literature comes this idea of an upper confidence bound or optimistic value estimate. So B plus is the optimistic value estimate. It's the combination of the average return from simulations so far and an exploration bonus. So T here, capital T, is the total number of simulations I've run, and TA is the number of simulations I've run on this particular action. So if I've explored one action comparatively very little, then this quotient is going to be very big. For example, if I've never run the tomato simulation, but lots of the other ones, then this quotient is going to be infinity. And I'm really going to think at least once about the tomato. So taking the optimal actions according to this optimistic value estimate sort of balances attention between unexplored actions, like the tomato, and promising actions, like the apple and the banana, because they have higher average B hat. Yes.
But isn't this now again for a regular Markov decision process? Because you're kind of throwing away the history and you're also not taking into account the changing environment?
Like you can definitely run this method also in MSPs and stuff, sure.
Yeah, but like you just look at T of A's, like number of times that you've run this action, but it doesn't really matter.
Oh, no. Okay, sorry. It's not the number of times you've taken this action, it's the number of times you simulated this action in your mind.
Oh, okay.
Yeah, sorry about that.
Okay.
Right. So, I mean, it's a pretty cool algorithm. It works really well in practice, especially in Go. That's the general idea. Put your attention where it matters. That's this sort of math justification. That's about approximating the planning part, expect the max. So what about approximating Solomon induction? So, as I said before, right, these environments, history-based environments, they allow for arbitrary long dependencies, which is good, because like if I dig down the treasure now, I can find it 10 years later. But like usually, in most contexts, like in practice, what I see most recently, like my last actions, and most recent actions and percepts are usually more relevant when predicting what's going to happen like the next minute or so. So, yeah, for example, this is my view 1 week ago, this is my view right now, and this is going to be more useful for predicting what's going to happen the next minute, this view. So I call this like the most recent bit of the history, the context. So in this case, for example, last 2 percepts and last 2 actions. That's the context. And I'm going to claim that in practice, usually the context is the most relevant thing for predicting the next bit. If I want to throw away something of the history, I should throw away the first part and keep the very latest part. And this is just to make the whole thing more efficient.
Question.
Yeah, question.
So in
in the MCTS part, when you're doing the rollouts,
Uh-huh.
do you typically think about doing heavy or light rollouts?
Heavy or light, you mean random actions or some guided actions?
Yeah.
So far, what has worked best is just random rollouts.
That's odd, isn't it? That they
It is
found
odd.
that to be the case.
Yeah. Right, so when we have this context, which makes the whole thing more efficient, we can actually learn in a much simpler way. So for example, say my most recent context is 0011, and I'll try to predict the next bit. Then I can simply look back through my history and find previous instances of the same pattern, 0011. And maybe I see that twice after seeing this context, I got a 1, and once I got a 0. Then it seems like a plausible prediction to say that the next percent is going to be 1 with probability 2/3, and it's going to be 0 with probability 1/3. Sort of very easy learning principle. Yep?
And what's about stochastic environment when observation never repeats exactly in exact way?
Right, so we always assume that the set of possible percent is finite. So in this case, with the most extreme state, it can only be 0, 1. Yeah. And in this case, it works. Yeah. So yeah, when we just assume that the most recent context is what's good for predicting, then we can have this easy learning principle. Yep.
How do you set the length of the...
Very good question. That's exactly my next slide. Actually, the next like 3 slides or so. It's a very interesting question. So, how long context should you have? Generally, if you have like a longer context, then you're gonna be like have more relevant things. You can have like more precise predictions, perhaps. But on the other hand, you're gonna have like less instances of this particular context previously in the history. So like a real-world example, if I'm going to a Vietnamese restaurant tonight and I want to predict how good will the food be, then I could choose to predict the experience with just previous experience with this particular restaurant, or I can base my prediction based on all Vietnamese restaurants I've ever been to, or I can base my prediction based on any restaurant I've ever been to. And like in the first case, I have like high precision, if you will, but I only have like a very few data points, especially if I've never been to this restaurant. It's completely useless. Perhaps the middle one is the most recent one. What is my general experience with Vietnamese restaurants? I get sort of medium precision and medium amount of data. But if I don't have much experience with that either, then maybe I should base it on any restaurant visit I've done in my life. I will have very little precision, but at least I'll have plenty of data. Yep.
So here you're, instead of looking at the whole history
Yep.
and asking which programs generate the whole history.
Yep. I'm forgetting all about programs. I'm just looking at the context. Usually in this kind of context, what is the next bit?
Okay, so what do you use for your 2 to the minus length multiplier when you do this?
Right. I'll get to that in my next slide, or maybe 2 slides. It's a good question. Right, so we have this like trade-off between having short context and we have more data, but we have less precision, or long context. In this case, we have less data, but greater precision.
A question?
Yep.
But the length of the context usually depends on the problem.
Exactly. So I'll get to that. Like, there's this interesting trade-off. Depending on how much data we have, it's probably, like if I, just in the beginning of my life, I don't have much data at all, so I should just use a short context so I have anything to go on. But later in my life, I have lots of experiences, and then I can afford it using a longer context and have more precise predictions. So the best choice of length of context depends on the amount of data. And it might also depend on the context itself. So this is illustrated with this example. Let's say I hear someone say a word, and I hear it's cup or cop, and I can't quite distinguish what it was, the similar words. But if I know a bit of the context, for example, if I know that the words just previously were filled there, and I can be pretty sure, certain it's cup, right? Because fill the cup makes no sense, but fill the cup makes a lot of sense. On the other hand, if the immediate context was from the, then it could be either, because both drink from the cup or run from the cup makes perfect sense. So depending on what the context was, I might want longer or shorter context. And of course, it also depends on which environment I am. So this is enough motivation. We actually have this really amazing context-free weighting algorithm, which so we call this kind of thing a context tree. And in like the sort of binary case, context trees looks like this. So for example, the leftmost says that you should always use a context of length 1. And the second one says you should always use a context of length 2. And the last two are like, depending on the context, you should use a context of 1 or 2. So these are like all the context trees of depth up to 2, right? So we can encode these binary trees. They're like standard coding techniques for binary trees. And I call it code length. So gamma is a tree, and the CL is like the code length of this tree. And a tree specifies what context to use in different situations. So it gives probability for some precepts, given some actions, just like a program did. CTW is just kind of very similar to the Solomon distribution. It's just we use trees instead of programs. And what's really amazing is the computation time. So while Solomon distribution with computer programs took infinite computation time to get exactly, CTW only requires constant time, which is like, yeah, the opposite. The computation time, so like you have to set this maximum depth of the context trees. And the computation time goes linearly in how deep you want the trees to be, how deep you want the maximum context considered to be. But once you fix one maximum depth of the tree, context can never be longer than say 10 bits, then your agent is like a constant time algorithm, which is what we want. We don't want the agent to require more and more computational power as it grows older. So putting these two things together, the context-free weighting algorithm and the Monte Carlo tree search algorithm, we get the MCI-CPW agent. It was implemented by Jules and S, and he wrote a paper about it in 2011, which is pretty good. So what this MCI-CPW does, practically, is that it learns to play Pac-Man. I should say that it cheats a little bit, so instead of watching the entire screen, which would be a very big percept, and it would be kind of hard, that the context would have to be very long, it sort of reduces the information a little bit, so they just gets to know what's in front of him, what's in back of him, what's to the sides, and smell food pellets. So basically it's just like a few bytes of information in the percept, instead of I don't know how many bytes in the whole picture. So cheating a little bit, it actually learns to play Pac-Man. Without knowing anything about the rules or what the game is, it just tries actions and sees precepts and tries to maximize the number of food pellets it gets. It learns to play Pac-Man pretty well. Also learns to play some other games, just by experimenting, taking actions, seeing precepts. Yeah. So yeah. So this the price we pay for this efficiency is that we have to assume that the context is what matters, not predicting. Things that happen before the context are not relevant. And this is not always realistic, and people have sort of tried to find ways around this limitation without losing efficiency. One idea is to like put loops in this like context trees. So you remember that this couple from the filter, and then what if you put a loop and like maybe you have then kind of like arbitrary long sequences for context, various ways, and that's like the looping subtle trees idea. You lose a lot of the nice mathematics using this, so then you have to rely on approximations instead. But it does improve performance in environments where you have long-term dependencies. Long short-term memory neural networks is another idea that I haven't quite been tried, but it's kind of a neural network which can store bits. So it would be cool to try an approximation based on this. The speed prior is Schmidt-Ober's suggestion for making Solomonov's distribution computable. It's still like double exponential computation time, so it's not really that efficient yet. Sort of the key component of this speed prior in Solomonov is in the sense compression. And there's actually a paper by Arthur at this AGI conference about making compression more efficient. So possibly this could also be a venue for making Solomonov induction more efficient. Yeah.
The granularity of your time slices, like
Uh-huh.
how long they are, must be a critical factor, because if you go too fine, then you can't go into the past much.
Yeah, that's right. Yeah.
So have you found some way of getting a sweet spot for that?
That's a good question. Yeah. I haven't thought much about that, but like, yeah, it's obviously a relevant aspect, how to do that, yeah. Right. Yep.
Why are you talking about Solomonov induction approximations? Probably it will be better to not approximate it, but make it more relevant to the reality.
Right.
Because, for example, Levin complexity doesn't approximate Kolmogorov complexity. Well, you can say that Levin complexity approximates the Kolmogorov complexity, but from my point of view, it's more relevant to the reality, because it's much less probable to observe data from sources which require more time to produce the data. So in this sense, is it good to talk about approximations? Probably we need not approximations, but more adequate statement of the problem.
Yeah, like that's obviously the idea, right? If you can be more efficient and more tuned to the real world, that would be really good. And as you say, Levin complexity is probably a step in this direction. But it's probably still too slow to be practically useful without further adaptations. Yeah. So let me also say something about feature reinforcement learning. So not that much time. So we have this agent and it sees these histories. And this is the same for humans, right? We take actions and we actually just get a sequence of percepts, but somehow we manage to infer states of the world. Like we generally think like, I'm at home, I'm at work, I'm tired. Like we tend to think about the world in states and plan from states. So it's a natural idea to try to get agents to do the same thing, even though it only sees a history. So feature reinforcement learning is this idea that we should find a map phi that maps histories to states. Yeah, this is just some examples where state representations are valid. I think in most environments there is some kind of state that generates history. Right. So when we're using like a robot with like some standard RL NDP application, then as designers we tell the agent this kind of percept means this kind of state. Perhaps a GPS signal or something like that. And the feature reinforcement learning approach or the phi-MDP approach So we should let the agent infer this map from histories to states automatically. So feature reinforcement learning, you could say it's an alternative to partial observable MDPs and to predictive state representations. Basically what happens is that the environment generates a preset. This is included in the history. The agent searches for a map phi that takes histories to states and tries to minimize some cost of this phi. Basically, how well does this phi predict the history? Or like the states generated by this phi, mapped by this phi, how well do they explain the history? And once you have this map phi, then you know what state you've been in, or at least think you've been in, and then you can use sort of standard MDP techniques, standard reinforcement learning techniques on this inferred state representation, and do all the learning and planning on those, and take an action based on that. It's a general idea. There's been quite a few works on this approach. It's like some theoretical results on asymptotic consistency on this inference technique. And then various like approximation, like it's obviously computationally hard to find the optimal map from histories to states, but in small toy problems this can be done. Otherwise, you typically have to rely on some kind of multi-color techniques, for example, simulate annealing, so search this space of possible maps, you find some lookup minima. It's also possible to use a variant of the context tree weighting algorithm and to use context trees for states. That is called context tree maximization. The math works out similarly, so you get like similar good performance, like this constant time algorithm, which is nice. And the experimental performance is similar to the AGI-16 approach. Similar extensions, looking for context trees or looking socket trees applies here as well. Have structured MDPs, so instead of trying to infer a discrete number of states, you try to infer some feature vectors. For example, how bright is it? What's the temperature? A vector of features like that. There's also been some theoretical work on relaxing the Markov property for this state. It's called extreme state aggregation. You can find much more in the references. Finally, I just want to mention the model-free ICT approach. So, model-free methods, like both of the previous approaches, was feature reinforcement learning and MCXCW, they try to like find some model of the environment and then plan from that model and find the best action. What has been found in reinforcement learning is that model-free approaches are often much more efficient. So for example, I'm sure you've heard about Q-learning and SARSA. These methods actually don't really build a model of the environment. They just infer how good is this policy or how good is this action in this state. So they try to sort of learn the value function, the expected return from an action by induction. And this means you don't have to do any planning. Because if you manage to infer the optimal value function, then you can always act optimally with respect to this value function. There's been some work on this, and in particular by Everitt again, a model-free version of IXC learns to play Atari games, and this time actually watching the screen, sort of similar to what PQN does. So it's a pretty impressive performance in this approach, but hasn't been explored that much yet. I'm basically out of time, so I'm just going to skip ahead to my conclusion slide. You should ask me about all the other cool things. Right. So, universal artificial intelligence, or actually, sort of conditional theory for AI, it answers the question what is the right thing to do. And the answer is in form of this one-line equation. It's useful for inspiring practical agents, and also for predicting and controlling super intelligent agents. I'm very sad I didn't get to speak about that, but I'll speak more about that in my talks later in the conference. And identifying and addressing fundamental challenges like notions of optimality and exploration versus exploitation. Thank you. Any questions? Otherwise, appreciate it.
Regarding the short discussion about right reward function to how would you compare, for instance, self-preserving agent to the IC formulation and of course the original cybernetics formulation of autonomous agents?
Right. Yeah, actually isn't really self-aware in that sense. It's sort of a dualistic framework.
No, I said, for instance, self-preserving agent. You know, the
Are you filming?
well, the agent
Are you filming?
that wants to minimize surprise.
Somebody might be.
Minimize surprise.
Yeah, it turns out that's equivalent to Bayesian prediction.
Oh,
yeah.
I don't know
So that's the best theory of autonomous behavior that I know. So that's what I thought. I mean, it would be nice to compare. I'm actually writing a paper on this, so I was curious what you are thinking.
Let's discuss it more.
Yeah, so let's take it offline.
Yep. Yeah. Anyway, let's talk about it. Please.
Well, sitting down and watching on the wall